All right. Um, Now, I have been working on. Let me get this zoomed in here. So I don't know if anybody up here wants to turn off lights or anything, or up to you. Okay. And if you can all see fine, then it's okay. So, okay. Um, so I have been working on preparing the midterm exam as well as a practice one. Um, Not ready yet, but I promise it will be soon. At the very latest by Monday. Um, so once a practice one is posted on the site, I will send everyone an email. But what I can give you right now is some general information about it. Okay. Okay. So I have some idea of what to expect. Um, so, so this will be held in class on Tuesday, October 22nd. Review a previous class, October 17th. My plan is that on the 17th, like I did last week, I'll be present at the coast and teaching from there. So I'll be doing that on certain Thursdays during the rest of the semester. Okay, now, all right. So there'll be two parts to it. Okay. So the first part would be 5 regular problems, which doesn't really mean anything until I explain what the other ones are. So the kind of problems that are somewhat like what you've seen on the homework, except they have to be short enough so that they can be done in an exam setting, since you just have an hour and a half. But I can tell you the topics for these problems. So not necessarily in this order, but or at least the order which are covered in the book. There'll be a problem on the convergence. So in other words, how rapidly is a sequence converging to a limit as n goes to infinity, or a function converging to a value as h goes to 0. So you're giving an answer in big O notation on the convergence of one of these items. Floating point arithmetic issues. For example, in other words, like we saw in last homework, taking some expression that's going to have some floating point issue, such as cancellation or overflow, and rewriting it in such a way as to avoid that. Okay, the next one this gets into Lagrange interpolation. So given data, find a interpolating polynomial, or the interpolating polynomial, because it's unique, using Lagrange form. Newton interpolation, that I just covered last time on Tuesday. So finding the interpolating polynomial in Newton form by completing a divided difference table. And then finally, this is a topic that I'm covering today, interpolation error. So if you have a function and given a degree of interpolating polynomial, estimate the error in that polynomial. Give an idea of how large that error can be. Okay. All right, so that's it for that part. So I'm basically coming up with 2 problems of each type that are meant to be similar in difficulty. So one of them I'll put on a real test, and the other I'll put on a practice test. I like putting out practice tests, and I figure students appreciate them because one of the worst things is when class gets a test and then they come away from it thinking, oh, that was nothing like what I expected. well, now you know what to expect. So to try to minimize unpleasant surprises. But there's one downside to it. I just want to bring it up right now, and probably bring it up again. But it seems to bear one of those things that bears repeating. Don't do the practice problem on a real test. The problems will be different, like the different functions involved, other non-negligible differences. I've had it happen where someone will pretty much carry out what he did in the practice test on the real test, and like you're not going to get anything for that. It's meant to give you a guide as to what's on it. I'm not giving away anything. So it's going to sound way too crass, but don't be dumb, okay? Because doing that is dumb. Okay, so that's the first part of a test. The other part of a test, okay. So this is what I like to call the lightning round. So this would be questions on concepts. Probably, okay, so do not hold me to this, but it feels right. Probably 10 or so questions of this type. Now, I'm not going to put anything like this on the practice test simply because there's no need. You already have something out there that will help you practice based on the quizzes, the Canvas quizzes. So it's concept check quizzes in Canvas. So I would suggest you just look at those. Now, again, I am not going to in some cases, I might be nice and just take one of those questions verbatim. Don't assume that I will do that, but the questions would certainly be related. But yeah, really, that is the way to study for this, is look at those. Yes?
On the lightning round
yeah.
questions, are they going to be true, false, short answer, multiple choice, something?
Oh, let me fill that in here. Short answer. Okay. So, I don't want people guessing.
The ones that, say for example, you didn't get right. I mean, you give an answer sheet so we could know the right answer to that.
Oh, okay. So you mean like?
I got 10 out of 12, but I don't know the answer to the wrongs that I get. So.
When I grade the Canvas quizzes, I write a comment indicating what ones you got wrong.
Yeah, but what is the right answer?
Okay.
You write the right answer under it? I don't.
Well, I mean, I'll be happy to provide that information. So.
I know it's wrong.
Oh, okay, all right. I just want to make sure that wasn't being overlooked, but yeah. Well, besides, I'm not expressing any reluctance to provide that information. I'm sorry I haven't done it up to this time, but I will do that for you if you want.
So we don't make the same mistake on it.
Yes, I perfectly get your point. Yes. Yeah. All right. So, no, I mean, let me explain something here. The reason I am in the habit of simply just giving a feedback, pointing out what went wrong, is that when someone turns in a quiz early and I have a chance to grade it, then I don't want to give away the answer in that case. So, yeah, so I need your understanding about that. Now, after everything is done and graded, then, yes, there's no reason why I can't put that out. But the other thing I want to point out is, about these concept check questions in particular, I mean, you do have a source that provides the answers, because the questions are drawn directly from a reading. Now, in this case, for chapters 1 and 2, well, actually just chapter 2 because there are no quizzes from chapter 1. From chapter 2, I have, because for another instructor, another institution, he used the book, I did write up solutions for the chapter 2 material. So I can just take that and put it out there. I haven't graded the. I know I still have some quizzes to grade, so I plan to be doing those over the next few days. Okay. All right. So are there other questions about the test?
So we go at 5. So you don't put like problem that we have to do in MATLAB? You don't do that, right?
Oh no, because it's a test on paper, so dealing with MATLAB's too cumbersome.
Okay. So we don't have to do nothing in MATLAB for a test, just
Right. Yeah, there's all going to be on paper. Well, and then you'll see what the problems are like when I put out the practice test.
that.
Okay. All right. Oh, okay. Hang on, I might have something here that can help answer that. Okay. This actually is a file for a practice test. I have not released it because I still need to make changes to it. Also, there's problems I have to cut out. So that still needs work. But, oh wait, I don't have, sorry, it's not in this file. Hold on, I need to find the right file.
So the practice test is going to be blank.
Well, I put out 2 files.
Okay.
So the practice test has blank questions, and then a separate file that has the solutions to those. Yeah, so that way you can go ahead and try it before looking at the solution. Okay. Exam FP. Okay. All right, I think this is the right file. Okay. So yeah, I'm taking items from a previous final and adapting it to the midterm. But what I do is I will put certain formulas. So at the end of the test, so possibly useful formulas. So I'll have to go through this and strip out the ones that don't apply. Okay, for example, this one that is certainly relevant. Definition of divided differences. Interpolation error, that's going to cover today. Lagrange polynomials. Taylor's theorem. Things like that. My thinking is that these are things that can always be looked up. And even then, it's still on you to understand what it is I put on here. So I don't want someone's grade hinging on if they just happen to remember some little detail about some formula when it's a formula that they can be looked up. So when I put out the practice test, it will include this formula sheet, so you will know exactly what information will be available and not available. So at least you'll know that there are certain things you don't have to take the time to memorize. Yeah. I will try to get it out sooner because I have most of the material in the end. I got to make up another question. Okay. So, but I'm also in the next few days going to try to get homework 3 all graded. And then actually, as far as the schedule is concerned, okay. So. All right, so this up here is the last, only material up to this point today is will be included in the test. So this topic here will not be. As far as homeworks are concerned, okay. So this is the one that's going on now. And then the next one. Because now that thesis defense season will be ending tomorrow, I will have more time to get things graded. So I can get all that done in time for the test. All right. All right. Any other midterm related questions? Alrighty. Now, for the last topic related, the last topic it'll be in the midterm. It's not the last interpolation topic. So, about error estimation. Suppose that we are approximating some given function f of x with a polynomial Pn of x that interpolates f at n plus 1 points. x0, x1, xn, so that this polynomial at each x is equal to f. So f and the polynomial agree at these n plus 1 points. So at these points, the polynomial and f are an exact match, but how accurately does this polynomial approximate f at other points? So just because it's an exact match at these points, you'd like to assume that you can then plug other x's into the polynomial and have a decent approximation of that value of f of x. And that's what interpolation is. Inter meaning between. So we want to try to have approximations of values of f in between all of those x's, as opposed to extrapolation. So extra meaning outside. So let's suppose that these points are in increasing order. So evaluating can't spell apparently. Between x, stupid LaTeX editor. Okay, so valuing between x0 and xn is interpolation. Whereas evaluating at points outside the interval x0, xn is extrapolation. Generally a bad idea. I would not recommend that. So for example, if you're using, suppose you're approximating the exponential. Actually, I'll show you an example of that in MATLAB right now. So I'm going to pick, all right, so I'll need to make a diary here. So let me make this bigger. Okay, so I'm going to pick a few x values. Let's just say 0, 1, 2. And the function I will approximate is the exponential. Now, I can get the polynomial that approximates the exponential. And I have 3 points, so that would be a interpolating polynomial of degree 2. So this function, so 1.4762x squared plus 0.2420x plus 1 is my quadratic function that will match e to the x at x equals 0, 1, 2. So what I will do is I'm going to make a vector of x's between 0 and 2. And then I'm going to have two sets of y values. First, I'm going to plug these into my function, the exponential. So those are my exact y's. And then I will evaluate this polynomial a polynomial p at these same x values. So y1 is the exact, y2 is the approximation. Here I'm doing interpolation. So let's plot and see what they look like. So I'll plot the exponential. Stop that. Okay. Then I will plot the polynomial in red. They match pretty well. And you can see there's some error in there. I'll show you the error formula in a minute to show you, get an idea how much. But it's not so bad. And notice at 0, 1, and 2, exact agreement, there's error in between those points. Okay. Now, extrapolation. I'm going to do the same thing, except I'm going to pick a range of x values that goes beyond 0 to 2. So I'll go up to 10. I will evaluate these again. I'll clear the figure window, and I'll plot my exponential. Notice it's growing very rapidly. It's a lot steeper now. And then I'll plot my polynomial, a quadratic. Well, that didn't go so well. Here in red is the quadratic, way down here. Because I was only trying to match a function between 0 and 2. I go beyond that, they're not even close. Orders of magnitude apart. Forget it. So it's important to try not to extrapolate. Interpolation works pretty well, although even then, not always, as you'll see. But extrapolation's almost certainly a bad idea. Okay. Now, I want to recall a result that you have seen before. Okay. It's called Taylor's theorem. And that says that your function f of x is equal to x naught plus f prime x naught, and so on. So the general term in the Taylor polynomial is we have the nth derivative at your center x naught over n factorial times x minus x naught to the n. So everything I've written out up to this point is the nth degree Taylor polynomial, and what follows is the remainder, Rn of x, where I'll write out the remainder separately. So that's equal to, basically it looks very much like the next term in the Taylor polynomial. So I need to change n to n plus 1. Okay. Now, the difference is it's evaluated at an unknown point, c. That's between x and x naught. Okay. So we're approximating f by a polynomial degree n. It's not the interpolating polynomial because it's focusing everything at x naught. But we'll notice we have n plus first derivative at some point. We have n plus 1 factorial. And then we have these factors, n plus 1 of them altogether. In this case, they happen to be the same. Now I'm going to show you the error in polynomial interpolation because it's going to have a very similar appearance. So f of x minus p n of x is this error formula. Okay, so I'm going to paste the same thing because I can just tweak it. Again, it is the n plus first derivative at an unknown point over n plus 1 factorial. So that part is exactly the same as the Taylor remainder. But we have x minus x1, x minus x2, etc., all the way to x minus xn. So it turns out that if the interpolation points x naught, x1 up to xn all collapse to x naught, this would be exactly the Taylor remainder. So there you have it. This is the error formula for polynomial interpolation. Now, this will be useful info for a test. How do we use this error formula to get an upper bound on the error? Because we're not going to get the error exactly. That's not reasonable to expect, because again, we could just have the exact result. So here's what we do. Okay. So this unknown point xc, so it's an unknown point in the interval containing all these interpolation points. Bless you. Okay. So we don't know anything else about it. So we need to determine how large this n plus first derivative can be on this interval. So containing all of those points. Now, in some cases, that's not hard to determine. Like, for instance, suppose there was the exponential. Well, the exponential is an increasing function. So if these are the points like in order, increasing order, I'll just plug the last one in, and that's a upper bound on that derivative. Okay, and I should also mention, since, of course, this derivative can be positive or negative, we really want to look at absolute value, okay, because it's the magnitude of this error that we care about. Second, you determine how large this product of linear factors can be. Again, an absolute value. On the interval containing these same points, your x naught to xn. Now, one point I want to make about both of these steps is required techniques from Calc 1 to find max min of functions. Who can remember from Cal 1? How do you find the maximum or minimum of a function? What do you do? Take a derivative. set it equal to 0, find the critical points. And here we're trying to find a max min on an interval. So when it's on a fixed interval, what else do you do? Yeah, test the endpoints. Yeah, test the endpoints of the interval. So yes, all that stuff that you were taught in Cal 1 ends up being useful here. And we look at both the max and min because it's absolute value. So whichever one is larger than absolute value is the maximum. So there will be a problem involving this on the midterm. So then on the practice one, I will put out a solution. Also, I will refer you to one of the examples in the text, 742, where I actually do carry this out, coming up with a bound on the error. Okay, but there will be more examples forthcoming. Okay. So the problem is, like, especially now as n gets large, this number n plus 1 factorial gets very large, and that's in the denominator, which is nice. So at least that part will get smaller and smaller. But these other pieces, the n plus first derivative, and this product of linear factors, that could conceivably get large. Now, here's a... okay, so... polynomial interpolation can get error, can get very large. In particular, you should avoid high degree with equally spaced points. You might think, okay, that the higher the degree, you might think a higher degree polynomial interpolation should work better, that the more points you use, the more accurate your approximation will be, simply because it's agreeing with a function at more points. And you also think that whether points are equally spaced or not shouldn't really matter. But both of these assumptions are wrong. And there's a famous example that I'm about to show you called Runge's example. Runge is best known for Runge-Kutta methods for solving ODEs. So those of you who stick around next semester will learn all about that. But now we'll look at his example of polynomial interpolation gone very wrong. Okay. Right here. Actually, I want to show the caption too. Okay. Actually, I'd like to magnify it somewhere in between. Okay. So this is a function 1 over 1 plus x squared. So the solid curve is that function. So it's kind of a bell curve-like shape. And what I've done here is I've used, as my interpolation points, we're on the interval minus 5 to 5. So my interpolation points are just the integers. So minus 5, minus 4, minus 3, etc. to 0, 1, 2, 3, 4, 5. So I have 11 interpolation points. So I have a polynomial of degree 10. That's the graph in the dashed curve. Is that polynomial degree 10. Now notice it agrees with 1 over 1 plus x squared at the integers. It passes through the graph of a function at those points. The problem is, in between those points, it goes hog wild. It goes literally all over the place. So now near 0, it's not so bad, but away from 0, the error is extremely large. Like here, the error is nearly 2. So definitely unacceptable. So it turns out in general, if you're using a large number of points, if you make those points equally spaced, you're asking for this kind of trouble. So do not assume that just because you're using higher degree that necessarily means you're going to get higher accuracy. Okay. Fortunately, there is something that can be done about it. So you might think, okay, if equally spaced points, because equally spaced points is so convenient. If that's not going to work, what can you do instead? Now, before I mention that, give you a solution, one thing I want to point out is, notice this function 1 over 1 plus x squared is fairly smooth. But polynomials of higher degree tend not to be very smooth, because think of it this way. Polynomial of degree 10 can have up to 10 roots. So when you have a polynomial that has 10 roots, we can, in this case, we can see some of them here. There's a root there, and 2 more here. Having that many roots naturally leads to oscillatory character in the graph. So if you have a function that behaves very smoothly, like it's 1 over 1 plus x squared, like something that looks like a bell curve, a high degree polynomial, the graph of that would look nothing like that. You want to use functions that have the same kind of behavior in their graphs as a function you're trying to approximate. So a lower degree polynomial would actually do a better job. And at least if you're going to insist on equally spaced points. But if you're open to something not equally spaced, there is another way to go, but actually works well even for high degree. And that's where Chebyshev interpolation comes into play. Okay, so instead of equally spaced points, we can set these interpolation points, the x values, equal to the roots of what is called a Chebyshev polynomial. Now, here's a definition of a Chebyshev polynomial. Tk of x. Is equal to cosine of k inverse cosine of x. At least for x between -1 and 1. Okay. Now, I've just called these things polynomials, but that doesn't look like a polynomial at all. So you may think, what acid am I on here? So it turns out they really are polynomials. So I'll show you why. Okay. So consider the case, k equals 0. Well, we get t0 of x. So we plug in k equals 0 here. So we're going to get cosine of 0, which is 1. Thanks to whoever knows their trig. Because sometimes I'll ask for that in class, and everybody will be like, no. Or just shout out randomly 1 or 0 or whatever. Yes, it's 1. Okay. Now, t... Okay. Now we have k equal 1. So t1 of x. So we plug in k equal 1. So now we have cosine of inverse cosine of x, which is what? What? Yeah, because inverse cosine, so inverse functions, they cancel each other out. So you start with x, you take inverse cosine and then cosine, you get it back where you started. So that is x. All right, so the first two are polynomials, but that doesn't say anything about the rest. But here's how we handle the rest. Although I have to be careful here. I have assigned some homework problems. Ah, dang it. Okay. I can't work it out in full because I assigned it for homework. What was that? That was an exquisite whine. Okay. All right. All right. So I won't give any information beyond what's in the book. We use these trig identities. Okay. So sum and difference formulas for cosine. All right, so it's cosine of a sum and cosine of a difference. All right, somehow the cosine disappeared. Okay. That would be plus sine A sine B. So if you work with expressions like these for different values of k for playing a role of a plus b or a minus b, then manipulating these, you can you can work out this find the free term recurrence relation for Chebyshev polynomials, which is tk plus 1 of x is equal to 2x tk of x minus tk minus 1 of x. So here we can readily see that the Chebyshev polynomials really are polynomials, because knowing that the first two are, this says that each one depends on the previous two, and what are we doing? We're multiplying by 2x, and then we're subtracting off 1. So given that the first two are polynomials, this relation keeps them as polynomials. So that's an example. T2 of x, so that would be 2x times x minus 1, so that's 2x squared minus 1. And then T3, okay. Then T3 would be 2x times T2, which is 2x squared minus 1, minus the one before it, which was x. So that's going to be 4x cubed minus 2x minus x, so minus 3x. And then you can keep going. What's interesting here, I want to point out that the T2 has a leading coefficient of 2. T3 is a leading coefficient of 4. And as you can see, every time we get a new polynomial, we're multiplying a previous one by 2x, so that leading coefficient is always going to double. One of the homework problems is to prove that using induction. You'll like that. Okay. All right. But intuitively, you can see why from a recurrence relation. Okay. So I should mention this definition. I had to give this condition here. X is between minus 1 and 1. That's because the domain of inverse cosine is minus 1 to 1. It's not defined outside of that. There is a definition for Chebyshev polynomials that extends beyond minus 1 to 1, but that relies on hyperbolic cosine. But it's not something that we need here, so I'm not going into that. So. Okay. Now, see where I'm at in the notes. Oh, I'm almost to the end of the notes. Okay, cool. It's like, did I forget to cover something? Not really. Okay, so we may have some time. I expect we'll have some time for any homework questions you might have. Okay, now I started talking about Chebyshev polynomials because we want to do something about polynomial interpolation error. And I've mentioned that if we set xk equal to the roots of one of these Chebyshev polynomials, that somehow helps with interpolation error. So the question is how would it help? Okay. So the Chebyshev points are the roots of a Chebyshev polynomial. All right, so if I pick out a polynomial of degree k, and one of the homework problems is to actually come up with this formula, but I'll just give it here. So it's equal to cosine, cosine of, make sure I get, okay. Actually, I need to use xj here. Okay. All right. 2j plus 1 pi. Oh, something got messed up here. Cosine over 2k. And this holds for j equals 0, 1, 2, etc., up to k minus 1. Okay. Now, so notice they are, so these are not equally spaced, but notice the angles that are passed into cosine. Those are equally spaced. But, so in other words, if I were to draw a unit circle and plot these angles going around a circle, you would see equal spacing. But then we take the x-coordinate. So what happens is these points are clustered near the boundaries of the interval minus 1 to 1. Okay. All right. Now, actually, let's see if I can show you that really quickly in MATLAB. Okay, so I'm going to set k equal to, let's say, say 20. Let's make it more interesting. All right, so then j is going to be 0 to 19, or 0 to k minus 1. So my Chebyshev points are going to be cosine of 2 times j plus 1 times pi over 2 times k. All right. And then I'm going to save these just the angles in a variable also. TJ, these are thetas, so they're angles. Okay. Now, so what I'm going to do is I'm going to, since these are angles, I'm going to plug them into cosine and sine. Okay. Also, I want to take theta going from 0 to pi, but with a fine spacing so I can plot the unit circle. Okay. So now what I'll do is I'm going to plot cosine t and sine t. Okay. Here's my not to scale unit circle. Let me improve that scale a bit. So it looks more semicircle-like. Then I'm going to plot x, t, y, t in red circles. So those are, so this indicates the angles of the Chebyshev points. So you see we have equal spacing in the angles going around a circle. But now I'm going to plot the Chebyshev points, which are xj. And I want to plot them on the x-axis. So I need a vector of zeros. A really easy way that at least saves typing to get a vector of zeros that's the same size as this, just multiply it by 0. So it gives you the appropriate 0 vector. And I'll plot those also using red circles. And here they are on the x-axis. Let me make that bigger. So each one of these points on the x-axis is obtained by taking one of these points that's sitting on the circle and drawing a vertical line down to the x-axis. In fact, that's what I'll do really quick is okay, so for each one of these points, I'm going to plot a line, a vertical line. So it has xj, xj as the endpoints in x, because it's vertical. And then I want to go from y equals 0 up to, wait, I need to refer to that element of a vector. So xj is a vector. I want one element of that vector. And I go from 0 up to the y coordinate. Well, that is the element of yt. And I'll use magenta. Okay. Thankfully I didn't screw it up because all of this is impromptu. So we're taking these points that are equispaced on the circle, taking only the x-coordinate, that's cosine, and bringing that down to the x-axis. That is what, and because of the circle getting more and more vertical here, that's what leads to the points being clustered closely near the boundaries. So, in general, to reduce error from polynomial interpolation, having more points near the boundaries helps. And that makes sense considering Runge's example. Look where the error is worst, at the boundaries, because we have the same concentration of points near the boundaries as we do in the center. So what we can do is, if we have more points around here, that actually helps control the error. Okay. Now, so if I have my polynomial tk of x, and these are my roots, then I can express a k-degree Chebyshev polynomial as a factorization involving these roots. Because if I know the roots, I know the polynomial, because I have a factorization. Except, there's one thing wrong with what I've just written here. If I take these linear factors, and if I were to multiply them out, you should be able to tell what the leading coefficient will be. What is the leading coefficient of this if I multiplied it all out? It's 1. Because we have all these linear factors have a coefficient of 1. That's what's called a monic polynomial. Monic polynomial has a leading coefficient of 1. But these Chebyshev polynomials do not have a leading coefficient of 1. So how do I correct this? What scaling factor should I put here? Well, what do we get? T2 is leading coefficient of 2. That might be a way to say k. But T3 is leading coefficient of 4. It's going to keep doubling. What? 2 to the... Almost. 2 to the k minus 1. Yeah, 2 to the k minus 1 because t3 has 2 squared. Yeah, that's why. Okay. Now, what I can, but also we need to keep in mind that this is equal to cosine k inverse cosine of x. So, what do we know about cosine? Because what we care about is how large this can get. How large can cosine get? 1. So, because it's a cosine, dk of x is less than or equal to 1 in absolute value on this interval minus 1 to 1. Okay. So now, so here's a key point right here. Polynomial interpolation error. And that's, I'll be lazy and copy and paste it from above. Okay. Now, if we use for x0, x1, xk, the k plus 1 roots of tk plus 1, then notice this factorization here, except for the adjustment in, oh wait, sorry. I need to adjust my notation here. xn, the n plus 1 roots of t n plus 1 of x. This factorization is the same form as this, except for the factor of the power of 2 here. Then we have the following. And it's not cooperating again. Dang it. Okay. So the absolute value of f of x minus p n of x is less than or equal to okay. Whoops. All right. So in the absolute value, I'm going to have same fraction as before. Okay. And then notice, because this product of linear factors is the same as this except for this, but this whole thing is less than or equal to 1. Therefore, I can say that this product is less than or equal to 1 over 2 to the n. Because 2 to the n times this is tn plus 1 of x, which is less than or equal to 1. So if I divide both sides of that inequality by 2 to the n, I have this. Okay. So that's because, let me make this a little clearer. All right, so that's 2 to the n. Okay. All right. And I want to emphasize, though. Oh, dang thing. Stop it. I don't know why this editor thinks I would ever want an actual dollar sign. I've written nothing but math here. Mathematicians don't make money. Well, okay. In certain places they do. But, all right. So, only on this interval does this apply, because that's only where you can claim that this inequality holds. So, here I have product linear factors with the 2 to the n less or equal to 1. Therefore, just linear factors without the 2 to the n is bounded by 1 over 2 to the n. Okay. So, in other words, this greatly controls the error in polynomial interpolation, because before I had to worry about this derivative being large and this product of linear factors being large. Now I only have to worry about one of those things. I still have, this could still be large, but at least this part is quite small. And so as n gets larger and larger, this denominator is going to get really large, which will again help the error stay small. And the derivative can't really do much about that, but at least this is something. So it's not a total cure for the difficulties of polynomial interpolation, but compared to equally spaced points, it certainly helps. I don't recall if I have in the book another graph. Oh, no, I don't. Not here. Well, I can produce that now. So Runge's example with Chebyshev points. Okay, so I need, so actually I have my Chebyshev points, well, okay. Those are my Chebyshev points. Now, those are points from -1 to 1. I need points from -5 to 5. So, in this case, all I gotta do is multiply by 5. So, in general, if you're on a general interval AB, you need to scale and shift the Chebyshev points so that they fall within AB and have a right distribution in that interval. Okay, so I need some x's for plotting. Many x's between -5 and 5. So if I plot the original function, notice x plot's a vector. I need to do dot divide and dot squared to perform these operations on a vector. Okay, so there's my function, 1 over 1 plus x squared. Definitely not to scale. Now, my polynomial, so these are my interpolation points. So I plug those into a function too. And now my polynomial I call polyfit, that performs polynomial interpolation. So xj, yj. Oh, in this case, I have 20 points altogether. So my polynomial of degree 19. Wait. That's weird. Oh. I mean, because some of the points are so close together, it's giving me that warning. So we'll see how this goes. All right. But generally, however many points you have, this argument should be 1 less than that because that's the degree. Okay. So now I will plot on the same graph x plots and polyval of polyfit. Well, okay, I have a polynomial already. That's p. Okay. There. So blue is the original function. In red, we have the Chebyshev polynomial approximation. Now, I want to show on the graph, so xj, yj in black circles. Whoops, let me fix my typo there. Okay, The black circles indicate the points at which the original function and the Chebyshev interpolating polynomial agree. So they don't agree at 0. That's not one of the points, but they agree elsewhere. Notice, again, the clustering near the boundary. So on the whole, unfortunately, we have this error here that's larger than I would like. But in general, it's a much better, well, a zillion times better approximation than with equally spaced points. So, in fact, if I had gone 1 degree higher to include this point, that would be far better still. But this is what I get for doing examples on the fly. Okay, so Chebyshev points are a very popular choice of interpolation points, and even though they don't have the same convenience as equally spaced, at least we have formulas for them in terms of cosine. So they're still relatively easy to work with. Okay. In the book, I have the updated error formula for a general interval AB, not just -1 to 1, or when you're using Chebyshev points. Okay. Now, well, we have 20 minutes or so for questions about whatever. Well, within reason, I guess. Particularly homework, of course.
So you said you would get grades back to us on our homeworks and the quizzes.
Yeah, all of that as much as I can.
In 7.1.3, I don't know how much I can ask. I mean,
Okay.
to prove that, can we just give well, we can't just give an example because it's for all x,
Right.
right?
Yeah, I mean, an example might help you figure out how to say for a general case, but yeah, it's not what I want to see.
Okay.
Oh, so you might have an idea, but you're not sure. You might give it away or something, or.
Well, I did. I just don't know if this. I don't know if I did actually fix that.
Oh, okay. All right, so one general hint I will put out for everybody is that so proving that so if you assume that there are two polynomials in this, and you need to show that they must be equal for all x, a more helpful viewpoint is focus on the difference of these polynomials. Show that polynomial, that difference, must be equal to 0 at all x, knowing that it is equal to 0 at certain x's. And using the fact that we have polynomials here, what are properties that polynomials have. Okay. Other questions of any kind? We have a good amount of time.
Okay, 7.1.4.
Okay.
So, when
Okay.
what was that ask?
Oh, wow.
I'm trying to think how to ask. Okay. When you make the matrix system of equations and you basically can wait, I think I see what you don't just substitute in 0 and 1 for I. That means like the I is
Well, like okay, you are substituting x naught and x1 for x.
Right, for X from like that original, so then
Yeah. Yes.
okay, alright.
Yeah, because notice I mentioned here obtaining equally simple system of equations, because in the previous problem here, generally you're not going to have any non-zero entries in your matrix. This is designed so that you do have some zero entries,
Right.
and you want the idea is to accomplish the same thing at a higher degree. I will also mention that the whole purpose of this is to actually foreshadow Lagrange interpolation, Lagrange polynomials. Um, I think one of the most common mistakes I see on this problem is providing the answer in which the form of this interpolating polynomial, degree 2, is not actually a polynomial of degree 2 at all. It's got to be of degree 2. It's got to be quadratic. Because I get submitted things that are just a superficial generalization of this, but this is linear. Do not give me something linear, because it's just definitely going to be wrong.
You said, I didn't get that. Can you say it again?
Okay, so so when you move to this part of a problem and coming up with a form for P2 of x, what I've seen from past submissions on a problem like this, that some people will write down a form for P2 of x that's meant to generalize this, but it's not actually of degree 2. Like, for example, I've gotten submissions where someone will just add on a term to this, like a2 times a single linear factor. But that's going to be of degree 1.
Yeah. Okay.
Yeah.
I get it.
Okay.
That makes sense.
So you just simply put an x squared behind it? A2.
Like adding on to this. While that would make it quadratic, it will not meet the goal of making the system as simple as possible.
Like you could have it in the
Yeah.
like ax dx plus constant.
Because another way to think about it is, in this case, we were working with just expressing a linear polynomial in standard form. Constant plus another constant times x. Here we're working with the monomials 1 and x. So if I generalize to degree 2, I'd be working with the monomials again. 1, x, x squared. And that leads to a cumbersome system of equations. Down here, the linear factors were changed away from the monomials to get a system that was simpler to solve. So the idea is to do the same thing for quadratic. What does it take to make certain entries go away? Because whatever form you have, you're going to be plugging in x0, x1, x2. And if it was just 3 linear terms, you couldn't really do that. That wouldn't really help. But because they're quadratic, that actually gives you the extra flexibility you need to be able to get a simpler system. But you have to take advantage of that flexibility. So the idea is, what was it about this form that made things work out nicely? So what do that's somewhat similar to this, only quadratic? and working with 3 points instead of 2.
Moving on. Next problem.
You might as well do them all in order.
Might as well.
Okay.
Alright. Does the J matter if the J start at 1 or start at 0?
Oh, in here?
Yeah.
Oh, well, in terms of just dealing with notation, no, but like there have to be n plus 1 terms because you have n plus 1 points to fit. So wherever you start, wherever you index them from 0 to n or 1 to n plus 1 doesn't really matter, but there have to be n plus 1 terms.
So basically, it's at 1 then, because 0, so n start at 0 is 0 plus 1, so it's 1, regardless.
I'm not.
Because the value, would it change the outcome of the value? No, because it's 0, because as it say up here,
Yeah, it's only because of
I is not equal to j is 0, but if I equal to j is 1.
right. Okay. Yeah, but that's really independent of how the points are numbered.
True.
Yeah.
Because if it's equal to, if I equal to 0, cancel out. If I not equal to 0.
Okay. It's really just a matter of whatever indices you have, 0 to n or 1 to n plus 1, you're using the properties the Lagrange polynomials have of plugging in x values and the Lagrange polynomials being equal to 0 or 1 based on the index of a polynomial versus the index of the x value.
So we just, so in all, we're proving that to get a simpler formula, a unique formula. That's what we're trying to do with this problem.
Yeah. Well, the thing is, here, the focus on this problem is not about the uniqueness, because it's already been established that the interpolating polynomial is unique.
Yes.
It's showing that this actually works as that polynomial. That if I plug in this x into here, I get this y. That's the only thing you have to do for this problem.
Okay.
Using the properties of Lagrange polynomials.
I think
This is not the kind of proof that occurs in a real analysis class. It's less involved than that.
I think I figured it out before.
Okay.
But the next one, because we gotta go through all of that.
Okay. Well, I guess there are only 2 left.
We have the time. All right. It's number 4.
Okay.
For number 4, I'm confused of what we should do with very simple.
Okay. So you're given this vector of x values, and the job of that function is to compute all of these for all j going from 0 to n. So you have n plus 1 x values coming in, and you're computing the same number of these barycentric weights. So you're going to have a loop. Actually, you're going to have 2 loops. So you're going to have a loop for computing each one of these. Inside that loop, you're going to need another loop to handle computing this product, because you have to multiply all these factors together.
So why I can't just use that formula at the bottom, which I'll already have.
Wait, this one?
Yeah.
Well, that's for the other problem. Yeah.
Oh, confused.
Okay. Well, I mean, this is what the problem says. That the job of this function.
Okay, so the top one is just that formula above only.
Yes. Yeah.
Alright.
Yeah.
And in the bottom one, kind of like repeating the same thing, but you then change the top formula to the bottom formula.
Well, I'm not really repeating anything, but yes. So the job of this function, this problem, is to evaluate the Lagrange polynomial at the given x values that are in xx using this. But to evaluate this formula, what do you need? The barycentric weights. And that's, so this function has to call this one. Yeah, so you're not going to duplicate that work. You're just going to call your previous function and get the weights and use them.
So I'm gonna make both the same loop, and then also you said at the bottom, do not define x as x1. So just have x equal to whatever the values of your all your x indexes are, right?
Okay. All right. So I'm not sure if this will answer your question, but so what happened?
7.8, right there we say 7.8 is not.
Oh, yeah, not defined. So the thing is, yeah, if x, okay, you're taking your x values from this argument xx.
Yeah.
So you're looping over all the elements of xx. With each one, what you first need to do is use a loop to check if this value of x, this element of xx, is equal to any of elements of this vector. And if it is, then this formula would not apply because you get a division by 0. But at these x values, we know what the result should be because we have these x and y values associated with each other. So then your result is just going to be that y value. Now, if your element of xx is not among these, it's not one of these points, then you use this formula. So for each element of xx, you need to perform that check first, and then if xx is not in x, then you use this formula. So it's 7.8. So that's, go ahead.
So in writing this formula, just think of it in writing this function. Should I think of it as just a straight Lagrange with barycentric? Just think of it like that. First.
Okay.
The barycentric is just the weight that makes the difference.
So this function is just going to do the weights. And then this function, it will make use of them in this formula.
Because the only difference, because I'm thinking the only difference of barycentric with Lagrange is the weight. That's the difference with the both of them.
Okay. Each function is implementing a different formula. Okay. There are 3 minutes left. I'm going to give some additional tips about that problem, that last one.
Yes.
All right, so 7.2.5. Okay. So for each element of xx, as I just mentioned, must check if okay, so I'm using this notation to refer to that one element, because going to handle all of them. Okay, so if xxi is not found among elements of x, use 7.8. Now, as far as the implementation of this in MATLAB is concerned, what I recommend, make a variable that is equal to 0 or 1, equals 0 if xxi is not among x, this is not in x, and equals 1 if it is. So the idea is, when checking if xxi is in x, update this variable. So after checking, use its value to determine if you need that formula at all. So the idea is, like, if I call this variable, I'll call it found, because that's what it means. It's one if you have found. You think of a Boolean variable, 0 or false if it's not found, a 1 or true if it is found. So as you're checking, if you do find this within x, you can set found equal to 1. So after your loop that is checking this, then you check. If found, we skip over this formula. If found is 0, we do need to perform this. So that way you're not doing extra work. So this is something where you may have like a verbal understanding of what you need to do, but that doesn't always necessarily immediately translate into code. So I'm helping with that translation process. Okay. Also, dang thing. Okay. Other commands related to loops. Break. The break command, I've shown you this before, exits the loop immediately. Whereas continue command will stop the current iteration and then start the next one. So in other words, for continue, you want to abort your current iteration, but you still want the loop itself to go on. So sometimes that can come in handy. Like if there's a portion of the loop body that you want to skip in a certain situation, you can use continue. So that's one that can be useful for this problem. And then, so break will exit the first enclosing loop and just abort it altogether. So these are loop-related commands that you should be aware of. I will not say that they are absolutely necessary for this problem, but you might find them convenient. Okay. All right. Well, it's past 8 o'clock, but by all means, keep questions coming. On homework, actually, I haven't been getting many. Could use more. Whatever I get, I will post answers of general interest on the site.
I'm gonna tell you, I might miss if I do.
I'm sorry, what?
I said I might not get the right answer to this, but I'm gonna try.
All right, well, do your best. I give partial credit.